Welcome everyone to the Infosys Chandrasekharan Random Geometry Colloquium. So we're very happy to have Jayadev Athreya give his second talk in this series of 3 talks on geometric counting problems and variance estimates. Please go ahead, Jayadev.
Thanks again for this opportunity to talk for several hours. It's always a pleasure, and it's always nice to talk to this an audience that's kind of big and diverse in terms of mathematical interest. In particular, if there are probabilists in the audience, I would love to hear, if any of this stuff rings some bells or looks similar to constructions from classical probability theory. We're always looking to build these kinds of connections, and we'd be very interested I'd be particularly very interested to understand more about about how the work we're doing relates to the stuff that probabilists are doing. Okay, so the plan was, if you remember from the first talk, which feels like a long time ago now, we were going to start by talking about the space of flat 2-dimensional tori, and then we're going to generalize to the space of higher dimensional flat tori and talk about some application. And we didn't quite finish that story. So today we're going to finish a little bit of that story. And then we'll go on to what I said I would do in part 2, which is to talk about something called the space of translation surfaces and talk about the Masur-Smiley-Veech measure and some counting problems in that situation, which again kind of generalize the 2-dimensional flat torus. So that's the agenda for today. Finish up what we said we'd do in talk 1 and start a little bit discussing what I said I would do in talk 2. Okay. So right. So this is at the end. So let me just maybe start again with some notation. So the problem we're considering is we're considering the space. Our space is, I think blue is nice. XD is SLDR mod SLDZ is the space of unimodular lattices in R to the D. Right? The identification, again, being a coset G SLDZ, is identified just to the lattice GZD. If we start with a bounded, compactly supported function on R to the D, imagine, for instance, the indicator function of a ball. E.g., F is, let's say, the indicator function of the ball of radius R centered at the origin. We define F hat of, I'm going to denote points in XD by lambda for lattices. F hat of lambda is summation over all the vectors in lambda prim, F of V. If you prefer to think of this as if lambda is, I use lambda as say GZ to the Z, if lambda is equal to GZ to the D, this simply means summation over all primitive vectors in Z to the D. That is vectors whose GCD is, and if you remember right, ZD prim is equal to, let's say V1 up to Vn, where the GCD is equal to 1 of all of these guys is equal to. Okay, so this counts with weights if you have a function f, the number of lattice points in the support of f with sort of, this is a kind of an average or a sum at least of f over the lattice. Notice this is a finite sum by my assumption of compact support for any given lattice. So this is a perfectly well-defined function. And we also had this, the other character that I forgot to mention is if we had mu d, which is the Haar probability measure on XD. So we take Haar measure on SLDR, which really you can honestly think about. It's not wrong to think about it in the following way. Take Lebesgue measure on the first D-1 columns, and then take something that's about as close to Lebesgue measure as you can get for the dth column, subject to this restriction that it has to make determinant 1 with the rest. It's morally speaking, this is, what I've described is certainly absolutely continuous. There's of course a density on that last sort of thing, but it's a reasonably well-defined construction. I mean, more precisely, I had mentioned last time that you take this Lebesgue measure on R to the D squared, D by D matrices, you make this cone construction, and then this mu D, I can in fact even tell you what the normalization of this measure mu D is with that cone construction. That's what I was writing down here on this previous slide. It's this 1 over zeta of d down to 1 over zeta of 2. Okay. So this is where we are. And last time we stated this beautiful formula of Ziegel's, which probably goes back in this context, at least, to Hlofka or Minkowski, which is that the integral of f hat d mu d over xd is equal to 1 over zeta of d, integral of f, the just Lebesgue measure on r to the d. That is, if you take the, for instance, if what does this say? It says, for instance, if f is the indicator function of the ball of radius r, this says the expected number of primitive lattice points of length less than or equal to r is equal to, not approximately equal to, is on the nose equal to the volume of the ball of radius r times 1 over zeta of d. And this makes sense, right? The probability that a randomly chosen integer vector is primitive is 1 over zeta of d. And then, the number of lattice points you expect in a set is the volume of the set, right? If you, for instance, have ever tried to purchase flooring for your house, and flooring is area 1, think of the tiles as area 1, a reasonable estimate for the number of tiles you need is the square foot area of your house, right? This is basically what all this is saying. Okay, and then I got to this point where we mentioned the result of Rogers for d bigger than or equal to 3. So this is a result that's true for d bigger than or equal to 2. And then I'll mention a result of Rogers for d bigger than or equal to 3. And I want to try and give you a sort of a unified sketch of proof of these two results. And then I'll notice conspicuously absent is d equals 2. I'll mention this result of a result of Fairchild that works in the case d equals 2, and also results of Randall. But here, what is Rogers' result in d equals 3? He says, well, now let's look, instead of expectation, let's look at the second moment. So let's look at something that will give us information about the variance. And he says that this is, in this case, it's 1 over zeta of d, integral of f dm over r to the d, quantity squared, plus, so notice it's exactly its expectation quantity squared. So if you actually want the variance, you move this to the other side. And then what I'm going to write now is just what's left is summation over all pairs of relatively prime, so kq, let's say in z2 prim, integral of f of kx q, f of kx, f of qx dx over r to the d. So it's you have a bunch of kind of lower order terms. In particular, I want to point out that actually, if you apply this to f being, let's say, the indicator function of the ball of radius r, you can actually compute this sum on the right very nicely. This remaining term. In fact, this is also in Rogers essentially. If you take a function f and then you replace it by what's called its spherical symmetrization. Think of the classical example is if you take the indicator function of a set and replace it with a ball centered at the origin of the same area, this quantity can only increase. That's a key insight that Rogers had, because this term on the right is kind of measuring correlations, right, between lattice points in some sense, or correlations of the function f. And kx and qx, for instance, if one of them is in a ball, if let's say k is the bigger one, then the qx is automatically in the ball, which is not true for kind of an arbitrary set. So replacing a ball centered at the origin. So replacing an arbitrary set with a ball means that this kind of right-hand side term only goes up. I see there's some questions in the chat. Is there generalization? Simple, say, Q groups. Yes. Oh, thanks. And Anish, this is the great thing about Zoom is that in the chat, these questions can be answered nicely. Yes. And this is exactly the Zigelveech formula And there's, yeah, absolutely beautiful generalizations of this. You're absolutely right in that this can be understood. Maybe I'll just make a quick remark. If you like to think about it this way, R to the D is G, if G is SLDR, this is a good remark to make. And Rogers' formula can also be viewed in a similar light. If G is SLDR, let's say N is the stabilizer of the first basis vector in R to the D, and gamma is SLDZ, what's really going on in Siegel's formula, one way to actually prove it is the following. You have G mod gamma here, you have G mod N, which is R to the D. I should probably be quotienting it on other sides. And then these guys have a common cover, which is G mod N intersection gamma, which is, in fact, N intersection gamma turns out to be SLD minus 1Z semidirect semidirect, sorry, Z to the D minus 1. That's not very hard to prove. And then what our construction of f hat is doing is it starts with a function f here, lifts it to a function here by just making it constant on fibers, and then you push it down to a function on x to the d by summing it up over fibers. Here, what's a fiber here? It's gamma mod intersection gamma, which is exactly corresponds to sort of the primitive vectors in z to the d. It's FLDZ, and so this then you would get f hat here, and then of course it's kind of tautological that the integrals are the same on either side, right? You're just unwrapping and rewrapping an integral in some way. So in some sense, this is what's called the Fubini. This is Fubini's theorem, essentially Fubini proof of Siegel. You can prove Siegel's formula using Fubini, but then you have to keep very careful track of constants. So that's a little digression. Hopefully that was not too digressive. And then this picture generalizes wildly, as you can imagine, right? If you want to look, for instance, in Lang's FL2R, he writes down similar formula in the FL2R mod FL2Z case, but makes the point that this is in fact sort of complete general nonsense, unwrapping and rewrapping an integral, and it's just Fubini's theorem. So Manuel, I hope that was a useful little digression for you. Okay, let me give you a slightly different proof, or sketch of proof of Siegel, and then I want to do a sketch of proof of Rogers in the same vein. So Siegel, let's start with if we believe the following. So let's black box that f hat is in L1 of XC mu D. So I know I said this at the last time, but I want to repeat this because it's actually going to be a very crucial idea. Then f goes to the integral of f hat d mu d over xd is a SLDR invariant linear functional on BC of R to the D. By the way, this black box is not terribly hard. It basically involves trying to understand how can a function get very large. Basically, for the compact support, well, the lattice itself would have to have lots and lots of primitive vectors in some small ball, and you have to estimate the probability the lattice has lots and lots of primitive vectors in a small ball, and that something is basically the product of the measures of the balls. So you can actually directly estimate this and prove this using tail estimates in a kind of naive fashion. But let me black box it for right now. We'll come back to this discussion a little bit. But now, so it's an SLDR invariant linear functional, which means that the integral of f hat d mu d, just by sort of Rees representation, has to come from the integration of f over rd with respect to some, let's say sigma, where sigma is SLDR invariant measure on R to the D. And with a little bit of work, you can show, so what are the SLDR invariant measures on R to the D? SLDR acts on R to the D transitively, except, well, actually with two orbits. There's the delta measure at 0, and there's Lebesgue measure, are basically the two things. So sigma has to look like some A times delta measure at 0 plus B times Lebesgue. And then it's doing a little bit of normalization. You see that A is equal to 0, And then, for instance, if you take f to be the indicator function of b of ball of radius r for r much, much bigger than 1, f hat is almost constant, and is almost constant 1 over zeta of d volume of the ball of radius r. This is by standard lattice point counting techniques. And then, so you get that this, what I call b, is just 1 over zeta of d. So that's the sketch of Ziegel's formula. Okay. Well, what about Rogers? Rogers is saying something about f hat squared. So let me actually generalize Rogers a little bit. So what do I mean when I say generalize Rogers? Let's start. And actually, this is something I'm quite proud of. I think, you know, maybe this isn't quite fair, but I think Rogers's work had been forgotten a little bit. And actually, I'll tell this story because Anish plays a crucial role in it. Margulis and I were thinking about some problems about dynamics of unipotent flows on homogeneous spaces, on the space of lattices. And at some point, we needed a result about finding lattice points in kind of small sets, or at least bounding the probability that a lattice didn't have some points in a set of relatively large measure. And Anish found this beautiful paper of Wolfgang Schmidt, which seemed to address a problem similar to the one we needed, but not quite the one we needed. And then in that, you know, Margulis kind of really dug through the references and found this beautiful 1950s paper of Rogers. And so in our 2009 paper, we kind of, you know, really mentioned a lot about Rogers. And subsequently, there's been kind of a resurgence of interest in these kinds of higher moment formulas that Rogers discovered. And I think that's something I'm actually very proud of. So one thing is that it's actually very, very useful to go back and read some of these classic papers. For a few people in this audience, I'll also make the remark that Rogers makes some really interesting and cryptic remarks in his paper. Including one where he basically claims, hold on one second. I want to just read this to you because it's actually quite interesting. He claims a kind of equidistribution result. Let's see, Roger. Yeah, so he's trying to compute an integral, as we'll see, on the space of lattices. He reduces it to computing an integral over a limit of a series of integrals over a certain torus, and says, oh, well, the limit of these integrals is clearly the integral over the full space of lattices I want to compute. I don't intend, in a manuscript in which I do not intend to publish, here, actually, let me just share the screen with you. Let's see, you share. Yeah. Okay, so you guys can see this. So he says, let rho of lambda be this function defined for all lattices of determinant 1. The mean value in question is defined to be this integral over this. Well, this is a lattice lambda, which has his lattice lambda of this theta is this one which has this omega along the diagonals, this diagonal term to make it lattice 1, and then this vector theta 1 over here. And then he says, oh, I'm going to integrate this function on the space of lattices over this, and then it's going to converge to the actual integral over the full space of lattices. And he says, in a manuscript I do not, in which I do not intend to publish, I've shown that if this is a nice function, you know, continuous compactly supported, then in fact that this limit exists and is equal to this mean value over the full space of lattices. And this also gives you a normalizing factor for this measure, independent of Siegel. This is actually the first equidistribution result on the space of lattices, or the first place I've seen it written down, where this is an equidistribution of a translate of a horosphere on the space of lattices. And so there's a lot to be gained from going back and looking at Rogers. I'll send some of these papers to Anish and he can send them to the list. I should also warn you that there's some things that are wrong in these papers, but it's really very rewarding to read Rogers' paper. Okay, so wasn't really a digression I planned on, but let me actually, I'm glad I did it. Okay, so let's go back and do this. Okay, so you guys can see my see the blank notebook paper again.
Yes.
Yes.
Okay, great. And now I want to prove Rogers, but what I'm going to do is I'm going to actually generalize Rogers to a slightly more Rogers generalized. So we're going to start with a function H now is a bounded compactly supported function on RD cross RD. We're going to define H hat of a lattice to be the sum over pairs of primitive vectors in H, in the lattice of H of V1, V2. Notice we're going to apply this to get Rogers' formula to functions of the form H of xy equals f of x, f of y, then H hat is what I had called f hat quantity squared. This is kind of a crucial little trick. Okay, so we're going to do this in more generality. Then let's suppose you believe that H hat is an L1 of xd mu d. This is, by the way, only true actually, well, actually the way I've written it for, if I'm doing primitive vectors, this is actually true for d bigger than or equal to 2. So in fact, it is actually true, everything I've written down here until now for d bigger than or equal to 2, which is the only case we care about. So let's assume this. It's not so hard to show this. For d bigger than or equal to 3, you do some tail estimates. For d equals 2, if you're summing for primitive vectors, you actually only you can only have one short primitive vector really in a two-dimensional lattice. Okay, so two-dimensional unimodular lattice. Okay, so if we have this assumption, then again, H goes to the integral of H hat d mu d over xd is an SLDR invariant linear functional on RD cross RD, or on BC of RD cross RD. I'll just slight abusive notation. SL linear functional. Okay, so it has to come from an SLDR invariant measure on RD cross RD. Okay, so what are these measures? Now things get, let's start with the d bigger than or equal to 3 case, because there's going to be a difference in the d equals 2 case. So for d bigger than or equal to 3, what remark 1 is that SLDR so acts transitively on pairs of linearly independent vectors. Pairs of linearly independent vectors. This is a good exercise in linear algebra. If you haven't done this before, it's basically just, you can take any pair of linearly independent vectors and have them be the first 2 columns of a determinant 1 matrix, right? That's all this is saying. So that's going to give you 1 orbit. And that's, okay, linear, if I take a pair of vectors at random in R to the d, just uniformly, then they are going to be linearly independent. So what we get from this is we get a contribution of some constant times the integral of kind of h of xy dx dy over r to the d. That's the only kind of preserved measure on this orbit, mainly because SLDR acts transitively, which means the space is a homogeneous space that has a unique kind of SLDR invariant measure, just from the transitive action. And then, of course, I have to understand pairs of linearly dependent vectors. But since I'm summing up vectors in a lattice, so okay, what would be something that's obviously, can somebody think of an invariant? If I have a pair of linearly dependent vectors, what's an actual invariant that's clearly preserved by the action of SLDR?
The rank, so the maximal number of linearly independent vectors among that.
So I'm just taking a pair right now. So I have a pair V and W of vectors, and they're linearly dependent. So V is equal to maybe some constant, let's say lambda times W. Is there on the screen a kind of numerical invariant to the the SLD orbit of these guys? So if I look at GV, GW, GV is also equal to lambda GW, right? So the numerical invariant here is just lambda, right? So the ratio is preserved. And since I'm looking at lattice vectors, the ratio has to be a rational number. That numerical invariant is a rational number. So this is, so for a rational number, let's say it's in my notation maybe k over q, then I'm going to get some term ckq over r to the d h of sort of kx qx dx. That's the invariant measure supported on the space of linearly dependent vectors. And then, of course, you have to figure out what these constants are. By the way, I forgot who said something about the numerical invariant. You're absolutely right in that when you look at higher moments, then there will be this dimension of the span of the set of the linearly dependent guys. Here, the span is one-dimensional because I'm only looking at a pair of vectors. So that numerical invariant kind of collapses, and we look at this slightly finer one. There, you'll have these higher dimensional, you'll have these spans, and you'll have sort of determinants of things or ratios of things in general. And what that will mean for us is that there are versions of Rogers' formula for higher moments, but they're much more complicated to kind of deal with. Okay.
Sorry,
and then, yeah.
Could you quickly, I get the second part. I don't understand the formula in the first part. You integrate over RD, this function in two variables.
Sorry.
Okay,
that's much better.
So you say they are almost
yes.
all are linearly, almost all pairs
yes.
are linearly independent.
Yes. Yes.
Okay.
Very good.
Okay.
Good catch. Thank you. Yes, that's definitely an integral over the whole space. And then, again, using a similar strategy of taking sort of functions that you think will have almost constant version, almost constant hats, you actually get that here in this case, C is equal to sort of 1 over zeta of D quantity squared. And here, in fact, surprisingly, you get that all of these CKQs contribute the exact same thing here. They all contribute kind of a 1. Actually, I might have made a small mistake here. There might be a zeta of D factor that I'm missing, but it's not super crucial to what I wanted to say. So let me leave that aside for a second. The crucial factor is this 1 over zeta of D squared. And then if you apply this to H, so this is essentially the sketch of Rogers' formula. I should also point out that Rogers actually gives formulas. Rogers' formula gives formulas for LP norms, P integer, P is an integer, and as long as P is less than the dimension in general. What I've written, Rogers also did, so warning, Rogers wrote down a formula for n equals 2, wrote down an L2 formula for D equals 2, but it is incorrect. Because he ignored, so it's easy to make this a mistake, but if D is equal to 2 and you're interested in pairs of vectors, you have to take into account determinant of the pair VW is an SL2 invariant. And so you have to stratify, even the linearly independent guys get stratified by determinant, and then you also have the linearly dependent guys, which you have to deal with. And Rogers didn't sort of carefully deal with this. So there's a mistake there. And I direct you to the papers of my student, Sam Fairchild, where she explains and corrects this mistake and generalizes. So gives the correct version and applications. So let me say a quick word about the application before I go on to, I realize I'm now 1.5 lectures into lecture 1. But let me give you a quick description of one interesting application. I'm actually going to state a slightly easier version of Rogers' formula for a slightly easy and an easier version of Siegel as well. Let's also define F twiddle of a lattice to be just the sum over all non-zero vectors. So that's F twiddle. And then Siegel in this setting, so this is, you don't restrict primitive. Siegel says integral of F twiddle d mu d is actually equal to the integral of F on R to the D, right? The average number of lattice points in a set is the measure of a set. And in this setting, Rogers, and now you really do have to restrict to D being bigger than or equal to 3. Otherwise, the formula is just, I should make a remark that F twiddle here is actually in L P of XD mu D as long as P is strictly less than D. So if and only if P is strictly less than D. So D is bigger than or equal to 3. Rogers proves the integral of F hat squared d mu D over XD is equal to the integral of F dm over R to the D quantity squared plus this summation KQ equals 1 integral of F of KX F of QX, this is GCD here, dx. And as an application, and I'll just state this for right now, Margulis and I showed the following, which I think is quite nice. We showed that the measure of the set of lattices in X to the D that completely miss some fixed set A is bounded by a dimensional constant, CD, over the Lebesgue measure. I guess I've been using M for that, the Lebesgue measure of the set A. And there are some assumptions. The assumptions on the set A is as simply as Borel measurable. So this just comes from essentially, this is a straightforward application of Rogers' formula, and then simply estimating what we're actually doing is, so Rogers actually shows that if you consider the number of, so if you take F to be the indicator function of A, that the expectation of F hat squared minus the expectation of F hat quantity squared is bounded above by this dimensional constant times the measure of A. And as any probabilist knows, this is enough to give you this, this estimate that you want, because what we really estimate here is the measure of lambda such that F hat of lambda minus the expected value of it, minus the measure of A, is bigger than the measure of A. That's, I can put squares on this. And then this gives me that this is exactly less than or equal to, you can, sorry, I think I've less than or equal to the expectation of this thing over M of A quantity squared, where this thing is just this, sorry. Resize this a little bit. There we go. And then, so we get this bound, and then this is just less than or equal to, as we just observed, CD measure of A over measure of A squared, and that gives you the result. So this is just a very straightforward application of basic probability theory, or Cauchy-Schwarz, or whatever you want to call it. But then as a further corollary, you get, for instance, this is estimating the probability that you miss certain sets. So you can use this plus the Borel-Cantelli lemma in kind of very simple ways to get results on things like, that for almost every lattice, so if you have, for instance, Q is a quadratic form, let's say it's a homogeneous quadratic form, and you want to solve, let's say, Q of V is less than or equal to epsilon, let's say irrational indefinite to start with, and you want to solve Q of V less than epsilon with V less than some epsilon to some power here, by computing the measure of these sets in R to the D, you can then use our results to about, well, this lattice stuff, this is a measure of the set of lattices that don't have that, plus Borel-Cantelli to get almost every sort of effective results of this type. So solving, equations like Q of V less than or equal to epsilon with V less than epsilon to some power, where V is, let's say, in Z to the D. You want to find integer solutions to things like this. I don't want to spend a ton of time on this because I really want to focus on the geometric counting problems, not so much these kind of number theoretic applications, but let me give you some references to this. There's a paper of mine with Margulis in 2018, but I'll just say it's a third paper of ours in the Journal of Modern Dynamics. There's work by Anish Ghosh, Dubie Kelmer, and Shucheng Yu. There's work by Kelmer and Shucheng Yu in this direction. And then there's some work, if you're interested in these kinds of problems, there's some work of mine with my former student, Yanis Konstantoulos, in groups geometry and dynamics on lattices in the Heisenberg group and similar types of L2 formulas there. And also we have some work we're still finishing up on symplectic lattices. And then I should also mention, very recently, there's some absolutely beautiful work by Dimitri Kleinbach's student, Michel Skendery, who's on the job market this year, as is Sam Fairchild. So there's a lot of very talented homogeneous dynamics people on the market this year. Skendery on sort of what are called successive minima. And also he has a joint paper with Kleinbach and Skendery on a very general framework for kind of Diophantine problems. Apologies if I've forgotten sort of important pieces of work here. I know all of this is being recorded, so it's always dangerous to do this, but these are the kinds of things I remember. So let me say that there's still actually, I think, a lot of interesting stuff to be done in kind of the lattice setting that involves integrating and understanding formulas where you integrate over particular subsets of lattices with maybe extra structure. So here there is already some progress towards that in the Heisenberg and the symplectic case. The symplectic case, I should also mention, there's also work of Kelmer and Yu there, and Shucheng Yu himself. But there's also like orthogonal lattices. So generalizing kind of Rogers's formulas to the situation that Manuel asked about in the chat, sort of different classical groups, understanding Rogers's formula in very general situations is, I think, a project that's very worthwhile. Anish and I have been thinking about this and talking about this, and it's really quite beautiful. I think there's a lot of beautiful things to understand in this story. So there's a lot to be done there about variance of counting problems for lattices with extra structure, if you want to think about it that way. And then there's a lot of interesting arithmetic applications. But maybe let me pause here and ask for some questions, and then I'll spend the last 20 minutes today at least setting up and defining the space of translation services, and hopefully stating at least the L2 result in that situation. I know I went a little bit fast on this lattice point stuff at the end. Okay, so am I okay to go to talking about translation surfaces? So now, 45 minutes or 40 minutes into talk two, let me start talk two. So let's go to translation surfaces. Okay, so let's go back to the two-dimensional torus, which, okay, the very first one was it's just a square with opposite sides identified, but we also said, oh, it could be some kind of parallelogram with, that's not a parallelogram, that's closer to a parallelogram, with opposite sides identified. And what we did to think about, to generalize in the first setting was to go to higher dimensional tori or polyhedra, perhaps, with parallel faces identified. But why did we, with sort of cubes, hypercubes with opposite sides identified? But we could have just increased the number of sides here. We could have kept the dimension the same and increased the number of sides. We could have said, well, what happens, for instance, if you take some sort of octagon and identify opposite sides? So maybe this a little nicer. So I might identify this and this and this and this. These guys and maybe these guys. Sorry, I realized I wrote 6 there. I meant to write 4. So I have these, this thing. What do I get when I get this? Well, first of all, notice when I did the torus, these four corners collapse to one point, but that point still had sort of total angle 2 pi around it. I got an actual genuine flat metric on the resulting surface with no problems anywhere. There's every point kind of looked the same. Once I folded it up and made the identification, I could have made the corner be wherever I wanted. I could have taken any two curves that intersect there, cut along there, and unrolled it. But here, there's going to be something a little bit different. Let's see, for instance, where this corner point goes. That's going to be the right side of 2. It's kind of this part of 3. I'm just identifying things by translation. It's the top of 4. It's this side of 1. It's this side of 2. And sorry, where should I go? Yeah, it's this. Oh, I missed that. So it's this side of 3. So it's this side of 4, and now we really are done. So again, each corners collapse to one point. And now what's the interior angle? Well, the inside angles of an octagon, I have not drawn a regular octagon, I admit, but the inside angles of an octagon add up to 6 pi. And okay, let's also see what's the genus of the surface. Well, when I identify everything, let's count the number of vertices. Actually, let's go back to blue because I think blue looks nicer. Let's count the number of vertices, edges, and faces. Well, there's one face, just the polygon itself. I had 8 edges to start with, but I paired them up. So there's actually only 4 of them. And the number of vertices, well, there's only one vertex. So V minus E plus F, which is equal to 2 minus 2 times the genus, minus 2. So the genus is 2 in this setting. Exercise, if you get bored in this, if you take a 2G-gon, or sorry, not a 2G-gon, if you take a 4G-gon, you get a genus G surface with one singular point. And you can actually compute the angle. The angle there will be 2 pi times, let's see, so I want the axis angle to be 2G minus 2, 2 pi times 2G minus 1. And so in this case, G is equal to 2, so the angle is just 6 pi. And if you take a 4G plus 2 gon, if you took a decagon, for instance, you would again get a genus G surface, but now with 2 singular points. So, but what is this kind of thing I'm getting? Another way to see, by the way, that you get a genus 2 surface is you kind of pretend to extend this out. And if you were to identify the opposite sides of the pink thing, you would get, maybe I'll just draw this in blue, you would get a torus, but you get this torus with this kind of blue square, which is kind of filled in with these pink thingies. You know, those pink things I've just drawn them. They're not actually there, but then I have to identify these opposite sides. In this case, it would be kind of 1 and 1 and 3 and 3. And when I pull those apart and identify them, I get this kind of genus 2 surface and this red point here, which has angle 6 pi there. So what am I actually getting? What is a translation surface? So one definition is it's simply a collection of polygons. Translation surface is collection of polygons in, I'm going to say C for right now, such that each side has a parallel side of the same length. Side of the same length to which it is identified by translation. It is identified by translation. It's a mouthful. And then, of course, there has to be some sort of equivalence. And the equivalence is going to be kind of cut and paste. If you can cut one of your pictures up and reassemble it into one of my pictures, then we're the same surface. But of course, this is, you know, a very unwieldy definition. It would be nicer if we had something a little bit cleaner. Let's think about what we actually get. We have some polygons sitting in the plane. We've identified things with translations. Translations are what kind of maps? among other things. They are holomorphic, right? They're much more, they're very specific holomorphic maps, but they are holomorphic. So in fact, we get a Riemann surface structure on our surface X. So we have a Riemann surface. And well, if you just think about dz as living on the plane, right? Just the one form dz, which tells you if you integrate, for instance, dz along a curve, it'll tell you, how far the curve went horizontally and how far it went vertically. But dz is invariant under translation, right? D of z plus c is dz. And I bet you didn't think you'd come to this talk and hear that the derivative of a constant is 0 is a crucial thing, but it is. And so you get this holomorphic one form. So omega is a holomorphic one form. So if you don't like this language, don't worry too much. Really, you'll be fine thinking about these things as polygons with parallel sides identified. But what it really is it's a Riemann surface together with a holomorphic one form. And what's the equivalence? Two Riemann surface, such pairs are equivalent if there's a biholomorphism F, say x1 to x2, and then that takes one of the one forms to the other. You'd like this even less, what is a holomorphic one form? To me, it's just something that looks like in local coordinates, sort of some, g of z dz in some local coordinates. And you can integrate it, right? You integrate, it's something you can integrate along curves, and that's what it spits out as numbers. But if you don't like that, you can also think of it as a section of the canonical bundle. Now that's not the language I think of it as, but that's perfectly nice. The canonical bundle is a holomorphic cotangent bundle, and then this is just a section. This is another way of saying that you can just integrate things on it. So for those of you who like algebraic geometry, what I'm doing is I'm saying take a curve and take a section of the canonical bundle. That's the thing. And then, especially if you like algebraic geometry, you're very happy because you're like, oh, sure, there definitely ought to be a moduli space of these things. That seems like a very kind of nice construction. So there is a moduli space of these things. Let me give you one last kind of very easy definition. If you have a surface, a translation surfaces also can be thought of as an atlas of charts to see away from a finite set of points, which whose transition maps are translations. Right, so what do? We have some topological surface. We have some chart here, and maybe some overlapping chart here. They get mapped to C. Oh, I should have used different colors. Let me use red for this guy here. So they get mapped to C maybe. I have different charts mapping. So maybe the red guy goes here and the blue guy goes somewhere here. And then of course I have this overlap, which maybe I'll just use black for. And then so there's a transition map on this overlap, and this transition map ought to be a translation. This gives a justification to the phrase kind of translation surface, right? If you say X surface in basic geometry topology, you really want to define that kind of structure. So you have some map to, charts to a space, and then the transition maps should be, say, if you want a differentiable manifold, the transition map should be differentiable. If you want a smooth manifold, the transition map should be smooth. Here, the transition maps are translations. So, and then, the zeros of omega of the one form correspond to, this bad finite set of points here, which correspond to kind of corners of the polygon. My God, my handwriting is really. Correspond to corners of the polygon. Okay. So, and the angles, if omega is kind of looks like in local coordinates near a 0, if it looks like z to the k dz, I think of that as up to a constant, d of z to the k plus 1. That corresponds to an angle of 2 pi times k plus 1 at that point, because z to the k plus 1 is a degree k plus 1 cover of c branched over 0, right? So the map sort of C to C, Z goes to Z to the K plus 1 is a degree K plus 1 covering map branched over 0. Branched at 0. So that's why you're getting this kind of excess angle, right? It's turning a sector of 2 pi over K plus 1 into a sector of angle 2 pi. So it's taking the whole 2 pi and making it 2 pi times K plus 1. Couple of quick remarks. If you add up the orders of the zeros, you get 2g minus 2. That's orbifold Gauss-Bonnet, or if you like Riemann-Roch better, it's your favorite theorem about Riemann surfaces. So now what we're going to do is we're going to consider a space. What we're going to do is we're going to fix an integer partition of 2g minus 2, say alpha. So we have, alpha is some alpha 1 up to alpha k, let's say. Summation alpha I is 2g minus 2. The alphas are positive integers. You can consider these things with poles, but right now I want to just consider holomorphic things with zeros, so not meromorphic things. It gets much more tricky to talk about the things I'm going to talk about. So right now we're just thinking about the alpha i's as all. Well, you can think of the alpha i's as greater than or equal to 0, whereas equal to 0 corresponds to marked points. But really for right now, just think about alpha I as being positive. And we're going to consider the space H of alpha is the space of translation surfaces with this 0 pattern, or this singularity pattern. So for example, the octagon that I drew, it lives in what I'm calling H of just 2. If you were to take a decagon, which I will not attempt to draw right now, the decagon ends up in H of 1, 1. It has 2 singular points, each of order 1. Some other things that you can draw that end up in H of 2. This guy ends up in H of 2 as well with the following identifications. And then you can draw more complicated surfaces, and they'll be in these kind of higher things. And then what I'm actually going to do, just by abusive notation, I'm going to consider my surfaces to have area 1. Okay, so the area is kind of well defined of one of these things. If you like it in complex analytic terms, I think the area is actually integral of omega wedge omega bar over the surface. This is defined to be the area. Notice that if you scale omega by t, the area scales by t squared, because what are you doing? You're just multiplying all the lengths of the sides by t. And then if you scale out something in R2 or in C by t, the area should scale by t squared. So area is kind of a quadratic form here. And actually you can make this quite precise. So what information do I need to kind of determine one of these surfaces? What do these spaces look like? Well, here I really need, this space, at least locally, kind of looks like R or each. I need to know what this thing is. I need to know what this thing is, what this thing is, and this thing is. Let me call this Z1, Z2, Z3, and Z4. So it's kind of C to the power 4 locally. Once I know those guys, the opposite guys are well defined. And then if I consider area 1 things, it's this kind of area 1 locus inside of to get these kinds of sides, and these are what I'm actually here. These are actually honest about local coordinates on the space. These sides are honest about local coordinates. More generally, what you do is you take the homology of the surface, rel the singular points. So there's k singular points. So this has dimension 2g plus k minus 1. You take a basis for this. Let's call it, let's say A1 up to AG, B1 up to BG, and maybe R1 up to RK minus 1. So you can take your usual A cycles and B cycles. Basically, what you want to do is you're trying to cut the surface up into disks, into polygons, along a bunch of curves. And then your local coordinates are simply omega gets into the integral of omega over the AIs, integral of omega over the BJs, integral of omega over the RLs, I guess. Oh, sorry. There's an omega there. RLs. This is just doing here. We're saying, oh, homology classes are relative homology classes. That is, we think about omega, as an element in relative cohomology. It's relative cohomology. If you don't like that language, forget I said homology, forget I said cohomology. Just think about cutting the surface up into polygons and telling me what those sides are as complex numbers. These are called, by the way, period coordinates. And just like in the torus setting, what we do is, remember, I'm actually not, we're considering, we won't consider the area 1 set H1 of alpha. So this is kind of by saying, okay, again, we just take the cone over it and we take the Lebesgue measure over this of this cone, the Lebesgue measure on H of alpha. So the measure, for instance, of this set in H1, excellent. Okay, so let me at least state what the kind of the result is, and then I'll talk about it more next time. So what is, first of all, what's the, so far we have a space. We have a space, I'll call it H1 of alpha. We have a measure mu, which I haven't yet said is finite, but it is, and that's a theorem of Masur, Smiley, and Veech, and so we can make it a probability measure. So we have a notion of a random translation surface. Literally just kind of pick these sides. If you want to think about Lebesgue measure on the sides, that's perfectly reasonable. Just like in the FLDR case. But what's the counting problem we care about? Well, given one of these surfaces, x omega, well, this has sort of this flat metric, right? Coming from omega, or this polygon. Let me actually just, I think an example is probably better than anything else. The things we're going to consider are trajectories that connect the singular points. So here's that. In this case, there's only one singular point. We're going to consider straight line trajectories that connect singular points. We're going to call that's, for instance, a straight line trajectory that connects singular points. That's a saddle connection. But so is this. Let me actually use the different color for this one. Let's use pink. So if I went sort of halfway there, that would also be a straight line trajectory that connects two singular points. So we say that gamma is a saddle connection because it connects saddle points if it is a flat geodesic connecting singular points with none in its interior. We don't want to talk about it passing through singular points. It just starts and ends. So there's a pink one. I could draw some more ones for you if you like, for instance. And if I went sort of a third of the way up there, that one is kind of almost horizontal. And then I can define the Holonomia vector. The Holonomia vector is, let's just call it Z gamma, is the integral of, well, what do? I integrate omega. That tells me how far I've gone horizontally, how far I've gone vertically. That's a complex number. And the set lambda sub omega of Z gamma, a saddle connection on X omega. This is a discrete subset of C. This is a discrete subset of C. That's a result of Veech, that it's discrete. And so now we can play very much the same game. So we start with F is a continuous compactly supported function in C. We say F hat of omega, I'm dropping the X, is the sum over all z in the set of saddle connections, f of z. For instance, if f was the indicator function of the ball of radius r, f hat would sort of counts the number of saddle connections of length less than or equal to r. That's a natural counting problem. Right? So you have this flat metric on the surface, you want to count these special geodesics. And now we have this beautiful formula called the Zigelveech formula, but really it's Veech who proved it, who proved that the integral of f hat d mu over h1 is equal to a constant depending on h, integral of f over c, f of z just dz. That's L1, that's the expectation. And then the result that I'll talk about next time is myself, Itwa Cheung, and Howie Mazer, where we prove that in fact, f hat is an L2 of h1 comma mu. So not only does it have finite expectation, it has finite variance. And I'll talk a little bit about how we prove this result. I'll talk a little bit about the history, because as many of you probably know, translation surfaces have become a very active and prominent area of research in recent years. And so I'll try and talk about how this fits into the context of what people have been doing. And then I'll spend the last half an hour next time talking about hyperbolic surfaces and some of Mirzakhani's work. All right, so I think this is a good place to stop. Sorry for going over time.
Not at all. Thanks for the lovely talk as always. So let's thank Jayadev. Are there any questions?
I have a very general question, and it's a bit embarrassing that I asked. But for the case of tori, I know that we examine this space because it has very close connections to number theory and so on. I actually don't know the space of translation surfaces. Is it of interest intrinsically and dynamically, or does it also, do we have similar connections to number theory there?
That's a wonderful question. So since it is a general question, let me also give you a kind of general answer. So of course, at this point, I've been studying it for 20 years, so I think it's of interest intrinsically. But let me give you some of the motivations of why people studied it. Here's a very, very, very simple dynamical system. Take a Euclidean polygon and take a frictionless point mass moving at unit speed inside this polygon. And then when it hits the side, it's elastic collision. So angle of incidence is angle of reflection. So you just play billiards inside this polygon. For a certain class of polygons called rational polygons, you can do what's called an unfolding procedure. When the ball hits the side, you think about flipping the table over the side and continuing the trajectory straight. And this process, if the polygon is what I called rational, terminates and produces a translation surface, and the billiard flow turns into a kind of linear flow on this translation surface, where the linear flow is simply just start somewhere and go along a line and keep going. And so understanding the dynamics of these flows is really important for this incredibly simple toy model problem in Newtonian mechanics, right? This very, very simple problem. And it turns out that this dynamics is actually quite tricky. It's kind of in an intermediate regime. It's not hyperbolic dynamics like geodesics law on a hyperbolic surface. It's not elliptic dynamics like linear flow on a torus. It's kind of intermediate. Giovanni Forni calls it parabolic. And that's kind of the term that's been come to use. And then what happens is studying the space of translation surfaces, with many things, understanding the moduli space of the whole space of translation surfaces turns out to be useful to understand individual points. So an individual point, and in fact, what we'll see next time is there's actually a group action on the space of translation surfaces. The group SL2R or GL2R acts on the space of translation surfaces. And that serves as a kind of renormalization dynamics for these linear flows. So it's of great interest from that point of view. So that's one motivation. There's other motivations coming from, again, very simple electricity and magnetism. These linear flows on these translation surfaces are also pretty good, are models of electron transport in the presence of a magnetic field on the Fermi surface of a metal. And then more, for me, this space of translation surfaces, if you consider all of, let's say, genus G translation surfaces, this is a very natural bundle over the moduli space of curves. It's the bundle of holomorphic one forms. It's an extremely natural bundle over the moduli space of curves. If you look at something called quadratic differentials, that forms the full cotangent space to the moduli space of curves. And understanding dynamics of the action of GL2R here and the geometry of this space is very crucial to understanding the geometry of the moduli space of curves, or the moduli space of Riemann surfaces, which is, I think, an object that's of great intrinsic interest. So yeah, so I think these are some of the reasons one cares about the space of translation surfaces.
Thanks.
Okay, are there any further questions? So maybe you could tell us just briefly why Veech would think about doing something like this?
Yes. So why did Veech want to do this? Well, Veech wanted to, Veech wanted to count. So we wanted to solve, so a classical problem, again, coming from, say, billiards, which is, you know, how many, if you have some billiard in a polygon, maybe like this triangle, you might want to know how many trajectories, for instance, start at, you could start a trajectory at a corner that end up at another corner. And that corresponds to a count of these Sala connections. So you could say, let's try and count Sala connections. But before you do it on an individual object, you could say, well, let's try and see if there's some kind of averaging that one can do. And so Veech wanted to study this averaging problem. He used, in the same paper he computed this, he also proved an L1 counting result. He proved that for if you integrate the counting result, the counting problem minus what it ought to be, that it in the limit that that goes to 0 in L1. I should say this paper of Veech is incredible. Like most papers of Veech, it's very difficult to read, but it's just called Siegel measures. But I think Anish has also looked at this paper. We looked at this paper when we were working on some of our recent work. It's got, I think, kind of infinitely many ideas in it. And it's kind of very much worth looking at. If you're at all interested in the subject area, I don't recommend it as the first thing you look at, but you can read it as some kind of oracular text. I mean, it's, you know, I probably could profitably spend the rest of my career reading that paper and trying to explain various small pieces of it. It's really a remarkable piece of work. And for those of you who like homogeneous dynamics, there's sections in it you can read purely as homogeneous dynamics things. There's sections in it about the actions of Fuchsian groups on the plane that if you don't know the T of translation surfaces, you can still understand it really beautifully. And there's some really beautiful results. So yeah, so Veech wanted to count. So he got an averaging formula. Next time I'll tell you about work of Eskin and Masur, and then this work of myself and Cheung and H.
Okay, thanks very much. So if there are no further questions, let's thank the speaker again. And look forward to next week for another lovely talk.